Okay, let's get started. Are there any questions about anything? Okay, so last time I presented this example where we have an integer n, and let's just say we want to make an array based off of that with n elements. And I said in class that it shouldn't compile. What do you think happened? It compiled. So I was very sure that this cannot compile because I've seen this before where the thing that when you're declaring the array, when you're creating the array right here, the thing, I'll just copy it over here to make it bigger. The thing inside the square brackets has to be something that's called constant or compile time evaluatable. So whatever that means that at compile time, the thing between the square brackets needs to be known. Okay, so whatever that is, so like a pure number or something that comes out of a simple calculation where it can be done at compile time, that has to be here. Can the value of n be known at compile time? No, why? Because it's user input. So that's why I thought, logically, that this shouldn't compile because it's not constant. It's not compile time evaluatable. So I mentioned this tool, but I really recommend using it. Even if you can't read assembly language, which is totally okay, it's great to try to figure out what is my compiler actually trying to do here. So what I've actually done here is, here's the file, and the compiler that we've been using the entire class is the one in the bottom right. So ignore this part. It's the one in the bottom right. The one in the top left is another major compiler called Clang, which is used in a lot of Linux and Unix systems. And the one on the bottom left is the Microsoft C++ compiler. And these three form the basis of pretty much most compilation. And you can see, you don't have to read what this actually is, but the Clang and the GCC compiler, they both compile this program, whereas the Microsoft compiler does not compile the program. And so we've actually just found, accidentally, a difference between major compilers. They're trying to implement the same standard, and yet one of them doesn't compile and the other one do. So the reason for this is that the Clang and GCC compiler provides something called an extension that allows us to actually compile this. And I've been actually looking over the assembly for this, and I don't understand why it compiles. It works. There's nothing wrong with it. It works like a normal program, but there's no evidence as to why this actually works, but I'm going to dig deep and understand exactly why this is the case. But here's the interesting thing. So the current version of Clang right now is Clang 7. I have it right now on Clang 3.4.1, which is an old version of Clang. If I change the compiler down to 3.3, it doesn't compile. So this is why being on top of modern C++ standards is really important, because changes like this do happen. So maybe you could have a program that depends on this value being compile time evaluatable, and if it's not, the program just doesn't compile. Whereas if you switch to a later version of the same compiler, now it works, and then there might be a silent bug. So that's why being on top of things is really important. Yeah.
That was one of my kind of questions, because when I asked you about doing the array n+1,
yeah,
and like doing the for loop, it's the reason why I asked that question is because I'd seen an example in one of the forums of people utilizing that, of making these growing arrays that just like grow with the cycles.
Yeah.
And I guess it's a new, relatively new implementation then, or?
I don't think so. So the question is, well, can we have these arrays just grow larger and larger if we need them? I am very sure, although now it's probably false because of this, that arrays can't grow in size. They are a fixed chunk of memory because it could have huge security issues if it were allowed to grow. We'll talk about a wrapper for an array that can grow, quote unquote, and we'll talk about how it actually achieves that. But arrays like this don't grow. There's no functionality to allow them to do so. But I want to talk about the so let's look at this again. So what are the indices, the valid indices of this array? Actually, let's just do a concrete example. So let's just say there are 5 elements in this array. What are the indices of this array? Like, what indexes can I go into for this array? 0 through 4. So suppose I do this without caps lock. Int I equals 0, I less than or equal to 5, I plus plus. And then let's just say, cout array of I. I'm not filling these with any value. Let's just make the array like this. So let's make this bigger, compile, and run. So this is really, really weird. So look at this. So how many values are we expecting to print right here in this loop? 6. So do we get 6 values? Yeah. So the first 5, they are valid indices of the array, right? Because 0 through 4 are the valid indices. The 5th one is the one that's wrong. Well, look at this. They're not all 0. So this is actually another problem that C++ programmers have gotten themselves into. When you have an array like this, it's not always initialized to all zeros. But consider this. All I'm gonna do is I'm gonna move the array from inside the main function to outside the main function. That's it, nothing else. It'll probably fail, but let's see. Now it's all zeros. So this is actually a weird concept in C++ where if you have an integer or an array of integers outside of the main function, it is defaulted to 0 always. Whereas if they are inside a function, they're not guaranteed to be initialized to 0. So you may have some issue, like if you're trying to read through this array and you're expecting it to all be zeros, you're not going to get all zeros. So understanding these quirks as well as changing versions of compilers is very important, and I recommend you keep tabs on that. Yeah.
Can you blanket initialize like all of the values in the array to 0?
Yeah. So right. So if you wanted to have things all initialized to 0 and you don't want to put things as a global variable, what you can do is you can just say int I equals 0, I less than 5, I plus plus, and then just say array of I equals 0. And so that initializes all of the indices in the array, and then you can carry on from there. There's a concept called dynamic memory allocation, which we'll eventually talk about, which will always, I think, so I have to check this, but I think it initializes everything to 0. So how many of you looked up that talk by Scott Myers that I mentioned once? So he mentioned in one of his other talks that his job is a professional explainer, as he calls it, and so he says that his job is to explain what the initialization rules for integers are. So even for integers, it's complicated. So just try to, whenever you have an array like this, go through it and set all its values to a default value. When we get to something called vector, it'll do all of that work for us, so we don't even care anyway. And I've always said that you shouldn't use raw arrays like this unless it's like an extreme circumstance. So this is just an educational thing, not for you to actually do this. But if you did have an array, I would recommend setting it all to 0. Okay, any questions about all of that? Okay, so let's get back to arrays. So what are arrays?
Memory block of contiguous data that is stored.
Yeah, so it's just a big chunk of memory where we have a whole bunch of some value. So we could have a bunch of integers or a bunch of strings or arrays of arrays, as we'll eventually see. We could have a bunch of any type that we want. So in this case, the one we went over before, we're making an array of integers. So a whole bunch of integers all in one piece of memory. So one gigantic block of memory. So in this case, there are 10,000 integers in this array. So we talked about this before, but the storage is that each element is contiguously stored in the array. So an integer, of course, has 4 bytes, let's just say. And so each of these chunks right here is 4 bytes. So 4 bytes, and then right after it is the second integer, right after is the third integer, and so on throughout the rest of the array. It's a contiguous block of memory. So this is a little more complicated when we talk about strings, so I'm just going to stick with integers for now because it's way easier to explain. So we talked about this before. The int on the front is just what thing is stored in the array. Test is the name of it, of course. The square bracket, just the square brackets themselves just tell you that it's an array at all. And the thing inside the square brackets tells you how many things are in the array. So I size, whatever value that is, that's how many elements are in the array. And so the size of the array is the number of bytes allocated for it. Usually we'll just talk about the number of things in the array. So in this case, there are I size things in the array. So we went over this example where tests here has 5 integers, and the volumes array down here has 10 doubles in it. So a double has 8 bytes, let's say, and so volumes has a size of 80 bytes, but the number of elements is 10 because we said D size is 10. Okay, any questions about that? Okay, so if we want to access a particular element of the array, we look at the corresponding index. So if there are n elements in an array, what are the valid indices of that array? Well, what's the starting one, always? 0, for whatever reason. What's the ending one? n minus 1. Right? Because it starts at 0, there are n things in it, so the last one must be n minus 1. There's no check in C++ that you're within the bounds of the array. So like the example I just showed you, you can just zoom past the end of the array and do horrible things as a result. So try to stay within the bounds of the array. When we get to vector, you have to do that, but with raw arrays like this, there's no check if you go outside. But if you want to set a particular index of the array, what you do is you put the array square brackets again with the index that you want to be set. So in the first example, right here, we're setting the 0th index of the array. So where is that in the array? Is that at the beginning, at the end, or what? The 0th index. It's the very first element of the array. And so now we're setting 79 to be at that particular index. So you may, I won't go into that. So yeah, you're just setting the particular index of the array. What do we know about the rest of the indices from what I just showed you a little bit earlier? Are they all zeros necessarily?
Not necessarily.
Not necessarily. If I declared it globally, then they are zeros. But let's just assume that everything else is zeros. So after this first line right here, what are the contents of the array if there are 5 elements, let's say? Well, the first one is 79, and the other ones are, assuming, all zeros, let's just say. Then test 1, we input something, and then we can do calculations. So here on the right side, I'm getting the value at index 0, which is 79. And let's just say the user enters 10 for the CN line right here. So it looks up the value at tests of 1, which is 10. And then what does test 4 be set to now? 89. And so did anyone try this line right here? What do you think you should do? It's actually not a compiler error. Well, actually, from what we have done, it could be a compiler error. But let's just see what happens. So let's just make a simple array like this, maybe not set anything, and let's just print the array like this. Do you think it's going to actually print the array?
Oh, no, it prints random weird things. Yeah.
So it prints whatever this is. So anyone know what the 0x on the front means? It's hexadecimal. Remember, base 16. So what do you think this is, this long bit after the 0x? It's the address. So the ARR in the front is actually the memory location where the array is stored. So in fact, the weird thing is that array, the ARR right here, is a reference. So remember when we talked about references, a reference is just the address of where the value is stored. So when we did the ampersand whatever, we're passing the reference along the memory location. Yeah.
Would that reference location be useful in any circumstances? Like actually doing this on purpose? Do this on purpose?
Yeah, it could be really useful because if you have a executable, then what could happen is if this is stored in the executable, then you know where this array is going to be allocated. And so what will happen is if you want to inject some code for a security vulnerability, you know precisely where all of the action is taking place. And so because of that, knowing the actual address is really useful. The weird thing about C++ is that we could write any data to any memory location, aside from details. We can write to any location we want. So I could actually hard code this value, this memory location right in my program and say, I'm going to set this to 0. Then I'm going to set 4 bytes away to be 0. Then 4 bytes, then 4 bytes, then 4 bytes to be set to 0 and emulate an array. Yeah.
Could you set the array to an address saying AR equals to something? Or do you do it?
Good question. I don't know. So the question is, can I set the array's reference to be an arbitrary reference location? I'm not sure. Let's see. So let's just say I try equals. Okay, I have no idea what happened there. Yeah, I have no idea what happened there. Let's see. Okay, so yeah, you can't assign to it. And now someone's calling me. So I think what actually happens here is that the address itself is a constant value and you can't change it. So that's probably why. Yeah, even for the simple things, it's hard to understand sometimes. So I entirely understand if you are frustrated with some of this stuff, because I certainly am. But yeah, I'm pretty sure you can't, but maybe there's some weird way you can. Yeah.
What if you try initializing it there, like put it in the same line you declared the array?
I don't think you can actually do that because here you're trying to set the array itself. Yeah, that wouldn't work. Yeah, you're trying to set the array itself right here. There is a way of setting the values all in one shot like this, something called an initialization list, but you don't have to worry about that. But here, yeah, I don't think there is a way to set the address or to change it, unfortunately. Other questions? Seriously, you guys ask like better questions than any other class I've ever taught. It's amazing. So keep them coming. Okay, so yeah, you can't change the address, I don't think. But if you tried to print it, it'll print the address of where the array starts. So we can do cout and cin to cin to a particular index, and then we can set the value there, and then set a different value if we want. So we can use cout cin like normal, as long as we put the array name, square brackets, then the index that we want. So the thing inside the square brackets, not when we're declaring the array, but when we're actually using it, like we're trying to get a value out or set a value in, that's often called a subscript. I use the word index, but it's the same terminology here. So, and the cool thing is that the thing inside here, not when we're declaring the array, but when we're using it, it doesn't have to be compile time evaluatable. So here, I could have a variable right here that could depend maybe on user input. And so I can just look up the value at tests of index I. Or I can have two variables right here and look up tests of I plus j, for example. Or I could just have a particular index like 3. So the thing inside, the numerical value in here has to be, is called a subscript. It has to be an integer or an integer type, something like that. You can't pass a double or anything like that. It has to be an integer because indices are integers starting from 0. In fact, if we try to access, so I just thought of a really weird idea. What if we tried to access array of -1? So like go back 4 bytes. So I'm not even sure if that would even work, but let's see. Did it actually work? Yeah, it just gave me a warning. So apparently you can. So remember, it doesn't do checks as to whether you go outside the bounds, whether you go below 0 or above the length of the array. So just be careful about this sort of thing, because this type of thing happens all the time. Because you may get a warning here, but you might not. So there's actually a principle in software engineering called warnings are errors. Okay, so even though our program was allowed to compile, it gave us a warning and saying, okay, you're trying to do something stupid right here. Try to fix it. I'm pointing this out to you. I'm required to compile it, but I'm telling you that you're probably not wanting to do this anyway. So whenever you see a warning like this, it means that there is something wrong with your program in some way. So obviously something like this, but there may be some weird case where you have some warning and it's not really evident right away that there's something wrong. There is something wrong there. So try to eliminate warnings if you ever see them. Okay. But if we wanted to print all elements of the array, what you usually do is you write a for loop, because we do know the size of the array, essentially. So if we know the size of the array is 5, for example, there are 5 things in the array, we start the index at 0, go to less than 5, not less than or equal to, I++, and then just print tests of the index at I. Super simple. What if I wanted to print the array in reverse order? And this will be your, actually I changed it, never mind. What if I wanted to print this array in reverse order? So starting at the last index, going down to 0.
Do I equals 4?
Yeah, so if I wanted to do it backwards, I would do I equal 4, which is the highest index, so that's good. And then what is my condition?
I greater than or equal to 0.
greater than or equal to 0. What's another way I can do this? Greater than negative 1. Yeah. So there are other ways to do the exact same thing, but the way I like doing it is to actually specify, I'm not sure why it wouldn't work there, to specify the actual starting index that you're starting at and the ending index. So I'm starting at 4 and ending at 0. Oh, yeah, I'm going to get to that. So what if I just did this? So I'm going to copy this in and do this. What do you think is going to happen?
You'll just print array 5.
It's just to print array 5? Oh, I need to declare my int. Oh, oops. Yeah. Copying and pasting code can be a pain. What do you think is going to happen? Printed a lot of stuff. So what happened here is, think about what this loop's doing. So it's looking at index 4. Is that a valid index 4? Yep, perfect. So then what happens on the update? It goes further. Is it now a valid index? It's not valid anymore. So it just keeps going, right? It just goes 4, 5, 6, because there's no stopping it now, because there's no mechanism to do so in C++. But so think about it for a second. So what is the range on an integer? So it's a signed integer. So it's roughly, say, 2 billion on the top end and negative 2 billion or whatever on the bottom. It's not really important. So we should expect like billions and billions of outputs before something before it wraps around to the negatives and then eventually comes from the negatives up to 0. Because if it's the maximum value and you do plus plus, it overflows to the minimum value, because that's how integers work. But setting that aside, are we seeing billions of outputs right here? No, so like a few hundred or something. What do you think happened? So what happened here is segmentation fault 11 is a little cryptic. What it means is that you're trying to access memory you're not allowed to access. So in memory, there are things that are called protected memory. So there are places in memory where you're allowed to write into, or there's nothing to say you can't write into, and there are places where they're reserved for some process. So like the operating system, for example, will occupy some slot of memory, and it'll say only the operating system can write here. Nothing else can write here. So what happens is, at each time you want to write to a particular location or read from a location, the operating system will check, are you authorized to access this location? If you are, then you're going to get the value or set it. Then it'll check the next one. Are you okay or not? What happened here is we must have hit a location where we're not allowed to read from it. And so therefore, we get a segmentation fault, meaning that the program just quits as a result. So what is the fix here? Do a minus minus. Because now we want to go from 4 down to 0, not increase. So just be careful when you are changing loops like this. Sometimes you may change the initialization and the condition part, but leave the update part unchanged, and it'll do the exact opposite of what you want. So that was the case here. So that if we do this, now we get the exact output we want. Negative 278537360, precisely what we expected, and then 4 zeros. Exactly what we wanted. Outstanding. So yeah, so when you're working with arrays like this, if you want to go from the top down, you start at the top index, greater than or equal to 0, I minus minus, and then just print the array at that index. Any questions about any of that? Yeah.
So you have an array that's a string, and then the memory location that's next the array, but outside of the array it's an integer, and you're printing it,
Okay,
but it's still
I see what you mean. So, great question. So what if I change this array to be of type string? So let's see what happens. So this program is supposed to behave normally. And so what happens here is that, so the reason I am talking about ints and not strings is that the situation with strings and objects in general is a little bit more complicated. So objects like string are, when you create an array like this, they are defaulted to something. So there's a reason for why that is. We're not there yet. So string defaults to the empty string. So empty string is the one, if you've seen it in the lab, is the one with no characters in it, which is why we see a bunch of lines right here with no output, because we have the endl here. So there's nothing printed first line, then endl, all the way through. Yeah, go ahead. Yeah, I'm gonna actually now extend it. So let's go to -1. I'm not sure what'll happen now.
He doesn't know either.
Yeah. So, yeah, go ahead.
Convert the integer that was there into characters.
Yeah, that's what I'm expecting to happen. Oh, okay, I think I know what happened. So the first 5 lines are obvious. That's just our program. Remember, I said that strings are defaulted to something. So only the 5 strings that we're working with are defaulted. Anything outside, are they defaulted? No, so they're just random data, maybe all zeros or whatever the case may be. So what happens here is that, so I'm not exactly sure, I'll have to look into it, but each of these locations right here, array of I, is actually an integer. So, well, it's the size of an integer. So it's reading 32 bits here, so 4 bytes. So then what's happening here is it's trying to read this, I think, as a character array. Because what a string has is a character array on the back end. So what I'm thinking it's trying to do is to convert this to a corresponding character array. But this is not 32 characters, I don't think. So I'm not exactly sure why it's printing, let's just see, 5, 6, 7, 8, 9. Why it printed 10 characters? So I'll have to look into this. But so strings are defaulted, yes.
So when you run the same issue with string, you guys
Yeah, so let's do our weird example where we had the plus plus. Oh God. So let's see what happens. Prepare for weird output.
Oh.
So now you can actually see, can we get a security vulnerability from here?
Yeah. Well, that was my next question is, could you put together a rudimentary keylogger with stuff like this?
Yeah, you can you can create a keylogger based off, not even a keylogger. Just write a program that runs on someone's computer and just dumps the memory contents out, right? And so if it just dumps the contents out, then you can sift through and see, oh, is the password stored at this location? Hopefully, if with a modern operating system, that's not the case. But you can see how this can be a weird problem or a very huge problem, because if you can just dump all the contents out, you can read it later. Isn't that a little scary? So please use this for good. Don't be evil with this. Yeah.
So that's just an error that popped up because you had a lot of
Well, the only error that actually happened was the seg fault at the end. All of this is just reading data inside memory. That's all it's doing. So, pretty scary, don't you think? And it just dumps all this information out, although it looks a lot useless for the most of it. So there's a reason for this. So, how many of you write in a language that's not English, or that has accents or whatever? So, remember ASCII? So strings by default use ASCII only. So if it reads some piece of memory that is not actually ASCII, whereas each byte of ASCII corresponds to one character, but sometimes with other languages, like with accents or whatever, you need 2 or 3 bytes to make up one character in that language. So the string is looking and going, okay, so maybe this character needs 3 bytes, but it prints 1 byte, then 1 byte, then 1 byte. And so now it prints 3 things in here. So that's why we're getting like these weird outputs right here. So if we wanted to be a little bit more crafty, we would need to use something called a wide character string. For security purposes, I'm not going to teach you about that. I want you to learn it yourself. But a lot of it is actual ASCII characters. And so we can actually read data out of the user's memory, although a lot of it is completely useless. Pretty scary, yeah.
I don't know why there's so many question marks.
Yeah, so the question marks, as someone asked, those are, I think, that it tried to read this byte and it couldn't actually read it. Or it doesn't correspond to a character in ASCII. I'm not exactly sure. I'm not a security person, far from it. But you can see how this could be a huge issue. But any questions about this? So are you going to stay within the bounds of your arrays? You better. Okay. Any questions about this? Yeah.
So if you really wanted to find what the information is, you can like see which index it is, then find the average of the array, right? You can count.
Yeah. So if you wanted to know like where this particular data is, just have your program try to output the address of that array. And then now you have you know precisely where this important data is. But of course, there could be data in different locations too. So, any questions? Okay, so that was a lot on that. But you may think, okay, well, I'm an error-prone person. I do things wrong all the time. I want to avoid this type of issue where we have this, where I do the wrong thing with one of these, or I have an off by 1 error here, or I don't initialize it right. So I have good news. There's a modern C++, as long as you're using at least C++ 11, which came out in 2011, you can solve this problem entirely and not have to worry about it. And that is something called a range-based for loop, which is probably my favorite part of C++, other than maybe auto. This is so amazing in that you don't have to worry about indices. You just don't care. Don't worry about the index. You don't have to do the array of a particular index. Don't care. Doesn't matter. All you have to do is just say, for each variable in the array, then do whatever you want with the variable. So how would we actually do this for our program here? So I'm just going to comment this out so we can actually compare how good one is compared to the other. So what you do here is you just say for string, so the type of each variable, let's just say var, in the array. So the colon here means in this structure called the array. And then we can just see out the variable, like that. No indices, doesn't matter. Which one's better, the top or the bottom? The top one's obviously better. Let's make it even better. Suppose I changed, maybe some new requirements came in, and I needed this array to now, instead of be strings, maybe we're storing user IDs, for example. So instead of storing strings, we're going to store ints now. Because user ID can be an int. What's the issue now? I got to change string now. What concept can avoid this issue? Auto. Now you have my favorite combination of things ever in programming. So now it doesn't matter what the type of the array is. I don't care. Just figure out the type for me and just loop over everything in it. So this is perfect. You avoid the indice issue, you avoid the off by one issue, and you avoid the issue with just the simple range-based for loop of having a different type here. Why might this be a better idea? So suppose instead that we really did have an int here. Which way should this go? So I want to short here. So what could happen is maybe for purposes of like storing it in a database or whatever. So how many of you have seen a password requirement where they tell you you must have like at least this number of characters and at most this number? So that's actually a security vulnerability of sorts because that tells you how many characters are being stored in their database. So let's just say we were working at one of these shady companies and just saying, I want to print the stuff inside the database. And then what could happen is, suppose it's stored as an int, but I'm trying to print it as a short. Or maybe we're getting it from the user as an integer and storing it as a short. What could happen? Well, let's see. An integer has 4 bytes. A short has 2 bytes, let's say. Then what's going to happen is going to truncate. So if I did a short here, there could be some truncation that happens. And I don't want that. So if I have a long user ID in here, it'll print a different user ID, and then that can cause an issue. Some companies, when they do a registration of users like this, when you register, the password is not truncated, but when you try to log in later, it is truncated. So trying to preserve the input is really important. So that's why I advocate auto here, because you don't have any issues, some silent conversion happening. Yeah.
When you say truncation with password storing, are you talking about like rudimentary forms of hashing?
Not hashing, but like literally just chopping off characters off the password. So it just says, oh, you entered the shorter password, it doesn't match what we got, so you must have entered the wrong thing.
Are we going to go over hashing in this class?
Unfortunately, no. Good idea for an assignment. Everyone can thank you later. Yeah. Oh, sorry? Yeah, so remember auto matches the corresponding type of the array in this case.
The array type is make.
So, you mean this auto or when? If I did it up here?
Yeah.
So remember the array, the type is the thing on the left. So if I put auto here, it doesn't know, did you mean a string array or an int array? It doesn't actually know. So there is a different way around this, but for what we know, you have to put the type here because it's not being set to something. What you could do is you can say auto array2 equals array, even though this doesn't actually do what we want. So you could use it in some circumstances like this, but when you're declaring an array, you can't. But again, there's a different concept called dynamic memory allocation. We'll get to that, and you can use auto there. But you can't here because it's not being set to something. Okay, yeah.
For this range-based loop, this is only used to output all of the contents of the array, right?
No. So what you can do is you can do different calculations. So you can like do int var2 equals var times 2, and then you can do anything you want in here. So the var right here is the value at each of the indices in the ascending order. So the great thing is that this gives you the value that you want. Very rarely do you need the actual index, like 0, 1, 2, 3, 4. You just want the value out. And so that's why the range-based for loop is so much better, because it gives you the value you want.
Is this the container you were talking about?
No. So this is not the container. But what happens here with the range-based for loop is that you can loop over a container in the exact same way. So if I wanted to loop over a different container, which we'll eventually talk about, you do the exact same thing. So this notation of going over a range, array, or some other structure is exactly the same.
So on this one, technically you could make the same mistakes and you could do var -1 or something like that.
No, you can't make a mistake like this because the var here is not the index, it's the value itself. So if the array had 79, 10, whatever, then var will be set to 79, 10. It won't give you the index here. Yeah.
I was gonna ask, can you loop over it backwards using this? Is there a way to specify you want to go backwards?
So is there a way to specify going backwards? No, unfortunately. So if you want to go backwards, you can do one of two things. Either use the boring old way and then just make sure your indices are okay. Or what you can do is use some technique to reverse the array first and then use a range-based for loop. But it depends on the circumstance. But there's no way of doing this in that order for native arrays. Okay, so we got some time. So yeah, so let's actually try to compile this because without all this stuff. So let's see. So I'm just gonna try to maybe let's do this. So I'm just gonna try to compile this, and it's gonna give me a warning. So what you need here is to say that this concept comes from C++11 because it's a relatively new feature. So what you need to do in your compile statement, does anyone know? So,
Use version.
yeah. So the way you actually do it is you put dash std equals C++11. So what this means is that C++11 is what is called a standard. So the std here actually means standard. So I'm setting the standard for the compilation to be C++11. So then if I try to compile, I get no warnings, woohoo. And so then if we try to run, then we get exactly what we expect to get. So then, yeah, so we can actually use this like normal. Yeah.
Do you have a standard list of like compilation options that you normally use? Would you normally use C++11.03?
Yes.
Or,
Yeah. So how many of you looked at 03 or 0 something for the assignment due on Wednesday? So one person. So there are compilation flags like this one that you can provide to say, I want the compilation to try to do this or do this. In this case, we're saying enable all C++11 features and then try to compile with that. There are other features like I want this program to be optimized to do these things, or try to optimize it as much as possible, or try to minimize the size of the file, the executable that's formed, or optimize it for this thing. So there are other flags that you can pass along to say, I want this program to actually do this. So I want this feature, then I need something like std equal whatever. If I want it optimized, I need to provide a different flag. So there are a gazillion number of flags that you can provide. The standard ones that I use are C++17, so that I get the most recent version of C++, and something called 03, which means that I'm trying to optimize this program as much as possible. Enable all possible optimizations. It increases compile time, but it makes the program run a lot faster. There are some other ones that I have tried before to get even more performance out of my code. So suppose that, so if I just compiled like this program can run on any computer at all, as long as you have the right instruction set. But it can pretty much run on any computer. But suppose that I'm only running it on this computer and nothing else. Then what you could do is you can get additional optimizations based entirely on the instructions that this computer supports. So what you can do there is you can set the architecture of your compilation by doing march equals, then maybe you're trying to go for a particular architecture, but the one I use is native, the one that's on this machine. But these are the standard flags that I use. I won't test you on compilation flags, but be curious. Try to think about what flags are actually useful in what circumstances.
So examples of other architectures would be like x86 or x64?
No, so like Haswell or Westmere, like actual CPUs.
Okay.
Okay, so I'll see you on Monday.